All right, this is 16.2, wave nature of light. Today we're going to talk about diffraction, primary and secondary colors and pigments, polarization, and the Doppler shift for light. I know we already learned about the Doppler shift for sound, so we'll give you a little equation for light. Very similar, with just a few little changes. All right, diffraction. In 1665, we had a scientist look at shadows and notice that the shadows were not the same size as the objects that pass them. So when my hand is really close to the projector, we see about the same size as my hand. When I move it further away, it gets bigger and bigger and bigger. And they also noticed that the edges of the shadows were full of colors. So if you look really close, especially when I get further away, you can see almost like a rainbow effect around a shadow. This kind of led them to thinking about diffraction and how light is bent, or light moves, how it's bent or how it's diffracted. Here is a picture of a reflected ray. We have a ray going in, and it hits an object, and it reflects off of it. Give you guys the same talk that I gave my physics one. You should be shorthanding this, not writing everything, especially since you have access to them. All right, so diffraction. An example of diffraction. If I'm talking and I have the door open, people can hear me out in the hallway even though they can't see me. But they can't really tell where in the room I'm coming from because all they hear is the sound coming from the door. This is because the door, as soon as it takes my voice and brings it out to the hall, acts like a source. So they know that it's coming from the door, but they can't really tell where I am because I'm just the source inside, behind the door. The man behind the door. This happens with light, too. It's not going to happen with the door and light because the door is much bigger. And so when light passes through it, light is so small that it's not really going to diffract around. It's just going to go in a straight line. It works with sound waves because the sound wave is about the same size as the door, so it's going to diffract around the door. To do this with light, we need really, really, really small slits. And when we do really small slits, I will do a diffraction laser thing with you guys later. And it's two razor blades that are really close together, and a laser light goes through it and actually causes a target pattern, which is pretty neat. So this is an example of diffraction with multiple slits instead of just one. Each time you have a slit like this, it's about the same size of that of light, so around the millimeter or micrometer size, somewhere in between there, on what it's looking at. And light is around nanometers, so it's pretty close to it. The light will go through, and each one of these holes is going to act as a source. So I guess the little dots are the holes because they're acting as sources. So these three sources of light are now producing the different sources, and they're going to interact. And where they cross over, they're going to have a line, and where they do not cross over, they are going to have a dark space. You get what they call fringes. In other words, target pattern, where you have constructive and destructive interference. They call it an interference pattern, or a diffraction pattern, depending on what you're looking at. All right, so refraction. And we'll talk more about refraction when we cover lenses in chapter 18, I think. So when light goes through a translucent object, it will bend the object because the light is now traveling through a denser material. This is the same idea as when you're mowing the lawn and part of your lawnmower is on the grass and then the other part is on concrete. That side wants to move faster than it's moving on grass. It kind of bends a little bit. This is the same idea. When you have light going from air into, let's say, glass, it's going to bend. What's interesting is it's going to travel through the glass and it goes back into the air from the other side of the glass. It'll bend back on its original path. All right, internalize. Internalize, shortcut, shorthand. Don't write everything. Gotta learn this for college. College is another week for you. Talk, flip, right through the slides. All right, so especially like this slide, a lot of information. Don't copy it all. Internalize and write down the important parts. All right, white light. It's made up of many different colors. Scientists originally thought that when they put light through a prism, the prism somehow itself had color, like stained glass. When you shine light through stained glass, it shows up pink or blue, whatever the stained glass is. To prove that it wasn't just the prism that had the light, they took two prisms. They had the first prism, white light went into it, and it split into a rainbow. And then the rainbow, they took that rainbow part and put it through another prism, and that prism put all the light back together, and white light shone out. If it was coming from the prism, it wouldn't matter that there was a second prism. It still would have been broken apart. So they proved that the light itself has all the different colors in it, not the prism. The prism just bends the light. Now, prisms use refraction to spread the light out, and that's because each color of light has its own wavelength. So if you're seeing blue wavelength, you're seeing that specific, like, 470 nanometers. If you're seeing red, then you're like 790 nanometers. Each of them is its own wavelength. So when it goes into the prism, it's going to get refracted at a different angle because it's a different length wave. So that's how you get the spread out part. Do you have a question? No. So the electromagnetic spectrum covers a very wide range of waves. It's all the same electromagnetic wave. We get radio waves, we have infrared waves, we get our visible rays, ultraviolet, gamma rays, X-rays. We have all these things that are electromagnetic waves, but the only part that we can see with our eyes is this little tiny section between 400 nanometers and 700 nanometers. So this is the visible light spectrum that we can actually see, down to 700 nanometers, which is right on the other side of it is the infrared rays. That's like the heat sensor type. And it goes all the way up to violet, and on the other side of this is ultraviolet. You get your UV light. All right, let's talk about color in the atmosphere. Now, since these wavelengths spread out at different angles, because they're different wavelengths, they can be spread out to make a rainbow. This is what happens when it rains. Your rain acts as a prism. These little spheres, they're spherical-ish or teardrop-shaped when they're falling. And with the sun behind it, it's actually spreading out all those rays. If you get enough water, you can get like a huge lens and you're going to get a rainbow. Now in the atmosphere, we see this every single day, at least if you're awake at sunset or sunrise. During the day, we see blue, and then at sunset, right on the edge of the horizon, we see pinks and yellows and reds. And that has to do with refraction as well. Our atmosphere acts as a huge lens. So here's our atmosphere, and here's the Earth. And we have the sunlight, it comes in, and if it comes in the middle of the day and goes to wherever you're standing, let's say you're standing right here, it's not bent very much. And that's because blue light doesn't really get bent that much. It's a very small wavelength, so its angle of refraction is very small. But if we're standing here at sunset, let's say the sun is just setting, so we're seeing it like here, right? This is the light side of the Earth. This is the dark side of the Earth. The sun's here. The sunlight comes in. What's my atmosphere here? And to come to our eyes, it's got to bend a lot. So its angle right here is a lot more. So the blue light is not going to be bent quite as much, but the red light, since it's bent more, we see the red side of that spectrum. Now, some of the blue has to do with the atmosphere makeup, but a lot of the sunset especially has to do with the angle of refraction, how the whole atmosphere acts as a lens and gets those colors to go into our eyes. Think about it. It's always at sunset somewhere. Very, very deep. No? Okay, let's go with color addition. Who in here is an artist? Likes art, does art stuff? No? That's good. So no one's going to tell me that I'm wrong. All right, color addition. Now, we're talking about light, not paint. So everything you knew about art class from 3rd grade, you can forget for this class. All right. The primary colors are actually red, blue, and green. Nope. Nope. Art's wrong.
You even taught me a song about it.
No, they're wrong.
Sing it.
Now we're talking about light here. We're not talking about pigments. So we're talking about the back of your TV. Now when they switched from the red, yellow, white plugins for your audio and your video, well now if you go to the big fancy TVs, they got red, green, blue. This is because the light signals going into your TV make up different pixels, and to get different colors, they use red, green, blue. Because we're talking about light, we're not talking about paint. I think this is why art and physics just butt heads so much.
But isn't physics technically an art?
No, it's a science.
But like,
Nope. It's a science. I'm sure you can use physics to make art. Definitely.
I'm talking about like, you know how like there's the makers?
No, like fine arts are your cooking and your theater and actual art and I think fashion design type stuff. But physics is a science, like a biology or a chemistry. They're completely, like I have a bachelor's of science, not a bachelor of arts. Okay, so our primary colors are red, blue, and green for light. We're talking about light, don't forget that. And the secondary colors are yellow, magenta, and cyan. And I looked that up, it's pronounced cyan. Not like cayenne pepper. So if we shine red and blue and green light, where red and green overlap, you're going to get yellow. Where green and blue overlap, you're going to get cyan. And where red and blue overlap, you're going to get magenta. Where they all overlap, you're going to get white. You guys want to see this? Okay, it's kind of hard to see because it's relatively small and I have to get it close to the board, but I will do my best. Okay, I have red light and blue light. If I put red light and blue light together, what should I get?
Magenta.
Magenta. So that's magenta. Yes? We agree? Magenta? Okay. If I put red and green light together, what should I get? Yellow? We agree that that's kind of yellowish? Okay, and then what's the last one? Green and blue. This one always messes me up. Okay, red or green and blue. What should we get? Cyan.
Oh, I like that. Ooh, I like that.
Okay, so if I put all three of them together, what should I get?
White.
White. All right, you can do this if you have two friends and you guys all have phones. Get one of those flashlight apps with the different colors, and you can shine them. You know, something. You can do that at lunch when you're bored. Okay. Now, what's interesting is that the primary and secondary colors of light are actually the secondary and primary colors of pigments. So these ones are my pigments here. So our primary colors for our primary pigments are going to be cyan, yellow, and magenta. These are the primaries for pigments. This is like your paint. So these ones, I have cyan, I have magenta, and I have yellow. These are all primary colors. If I put, I have such a hard time with these. If I put these two together, I should get blue. So you can see how that's kind of bluish. That looks better. That's blue. Okay, so these are two are primary pigments. This would kind of act like your red in paint, and this one kind of acts as your blue in paint, and then you have yellow. So then if I put these together, you should get your red. Does that kind of look reddish?
Yeah.
All right, and then if I put these two together, you should get green. And if we put them all together, you get black.
Oh, Joe. There you go. So nice and black. Yellow and so there's your book. Okay, so notice that they're flip-flops. The primary pigments are the secondary colors, and the secondary colors are the primary pigments. All right, and then this is the part that gets a little confusing for some people. It took me a little bit to figure it out. Look at the diagram here. In order to see something, remember that we're talking about light. In order to see red, it has to absorb all the colors and reflect only red. Because we're talking about light. Remember, when you see red, you're just seeing red light. When you're seeing yellow, you're seeing green and red light together. So this one has to absorb blue and reflect green and red so that you see it as yellow. This one's green, so it has to absorb blue and yellow. Right? I struggle with these two. It has to absorb, it has to reflect blue and yellow and absorb only red. And with blue, it's just reflecting blue and absorbing blue and green. Not yellow.
So
why did I say yellow? This is reflecting green, only blue, only red, and then reflecting those red and green. Okay. And this one's reflecting all of them, so it's white. Notice that the little black dots on the dice here, they're absorbing all the colors. So if we shine only red on it, these things reflect red, right? Red and green, red, and then this is white, so it's reflecting all of them. So when we reflect red on it, it's going to reflect red back to us. So they look red. These ones absorb red. The green absorbs red. The blue absorbs red. So they look black because they don't have any other color to reflect back because that's only got red that it's reflecting on it. It's on it. It's absorbing. So they look black. Then we have blue here. And these two, the yellow and the red,
absorb blue, so they look black in the picture. But green and blue are reflecting blue, so we can see the blue. And the white one we can see is blue as well because it's reflecting all the colors. Now, the green dye in this one should actually be black, which is why it looks a little bit darker than the rest of them, because the black is, or the green is a primary color, so it should actually look black. It doesn't look black in that picture, probably because it's a fairly blue-green color. If they had just used green instead of a blue-green, it would look blacker. But I just don't think they used the right color of green. I think it's some part. You can see that it's darker than the other two, but other than the blue and the white. But it's not. It should be black. I mean, it's probably because it has some blue pigments in it. All right, the next one. Oh, this one always freaks people out. Here we go. Polarization. Polarization is a lens, but you can think of it as a grate. Light is three-dimensional, and it just blocks everything except for one orientation of light. So if I put three-dimensional light in here, only horizontal light is going to come through. Or if I turn it the other way, only vertical light is going to go through. It acts like a grate. That's what my little pictures are. Now, if I had two grates, one that blocked horizontal and one that blocks vertical, or only lets horizontal through and only lets vertical through, it should block all the light. Now, what's interesting is that this projector up here has green light this way and purple light this way. I think it's probably magenta light and green light to make up the colors on this screen. So if I block one way of light, so I'm blocking the magenta light, I'm going to get green. And if I block the other direction, I'm going to get magenta. Wait, do that again.
What is this?
Black magic.
I know. Last year, my students called me a wizard.
No, it's not a...
Okay, now if I block horizontal light and vertical light, I'm going to get no light. So now it's completely black. I'm blocking all the light.
It's like it's still green.
I'm so insane.
This is the coolest thing we've been.
So purple light, green light.
I
Purple
want to
light,
do that.
green light.
Now
Now notice when I turn it right, kind of in the middle, it's letting half magenta light through and half green light through, so it just kind of looks grayish. But if I finish turning it, turn it this way.
Oh no.
Studying
Does it only work with those colors?
Just because that's what the projector is showing me.
Huh?
Up there in the projector, if you look at it, you can see green light this way and magenta light this way in the lens that I'm from my point of view. So if you want to look at it later, you can come stand here and look up there. But if it had, blue light one way and green light the other way, then that's what it would show. All right, so if you want to go, next time you go to the store and you want polarized lenses, take two of the same pair of sunglasses and turn them so they're 90 degrees. If they completely block all the light, you know that they're actually polarized and not just tinted. The tinted still lets most of the color through. It just changes the color to make it a little bit darker. So it reflects some of the light. With polarization, it only lets half the light through. So it's only 50% that gets through, which is why usually polarized is better. Also, when they polarize their sunglasses, the way they put them is they let horizontal light in and they block vertical to reduce the glare. Since most of the light that you see, the sun's here, it's going to reflect off of horizontal things and not necessarily vertical things. It's going to reflect off the ground or the table or your car. It's not really going to reflect off of something that's horizontal like a pole. That's not going to be quite as bright as the rest of it. So it blocks the horizontal light so that you can see a lot better without damaging your eyes. So here's an interesting picture. This is unpolarized light. This is three-dimensional. And you can see that when it goes through a polarized lens, half of it, well, everything that's not vertical gets blocked. So the vertical goes through. And then this vertical light, if you put another polarization lens that's 90 degrees different, you're going to get your
you're completely blocked. So that's where we can't see through it. Now, if you block it somewhere in between, there's actually an equation for this. Once it goes through the first filter, you're going to have 50% of the light. And then if you go through the second filter, the different angle between the first filter and the second angle will be this theta. Now, I don't think that you need to do this in your homework. I'm pretty sure I pulled this from my optics college class. But it's called Malice's law, and you can calculate it. But I don't think that it's in your homework. And you can do this over and over again. You can do it with 6 different lenses, all with different orientations. You just keep using this equation over again because this is the intensity before the lens. This is the angle between your lens and the previous lens. And then that is the final intensity. Usually they do percentages. So 50% of light goes in, and then only 25 comes out or whatever. I know people have to leave for BCC soon. The last little thing that we're going to cover is the Doppler shift, and both those equations are in the book. You should be okay with that. I just teach. I'm not like a professor. I'm a professor for that kind of stuff. I don't have enough time. I barely have enough time to keep up with everyone. Okay, here's the equation for the Doppler effect. It's kind of similar to our Doppler effect for sound, except for, we're using the speed of light here. So the Doppler effect will change with frequency or wavelength. Wavelength and frequency are the same. So the objects that are moving away from us are redshifted. As they move away, their wavelength lengthens, which means that their frequency is going to get lower. And we call that being redshifted, because the redshifted of the spectrum is the longer wavelength. And things that are coming towards us, since they're coming towards us, the wavelength is squished up, making the frequency higher. And since the blue side of our visible spectrum is the shorter end, we call it blue shifted. Now, it can do this with any of the electromagnetic waves. It can do this with radio waves, X-rays. And what's interesting is it'll do it with all of the waves. So all the radio waves and gamma rays and X-rays and visible light rays will be blue shifted. And all of them will be red shifted if it's going away from us. So the equation here is the frequency that we see, or the color that we see, if you want, is going to be equal to the original frequency, so what is the actual color of light that it's emitting, times 1 plus or minus the velocity of the object over the speed of light. Now, the speed of light is 3 times 10 to the 8. And the velocity that they're going, so if they're going away from us, we make it minus, because it's going further away. And if it's going towards us, we're going to make it plus. Okay, so we can do this with wavelength because remember it changes frequency and wavelength. Wavelength and frequency are related because the speed of light is always 3 times 10 to the 8. We were able to put it into this equation. So we can see that the change in wavelength, that's what this means, change in wavelength. So the original original wavelength, the difference between the original and what is seen is going to be the change. It's going to be plus or minus v over c, so the velocity of the object. Speed is c is the speed of light, 3 times 10 to the 8, and the original wavelength. And in this one, a positive change in wavelength means that it is moving apart, and a negative change means that it's moving closer together. So they're backwards, I believe. It's a positive change for moving apart. Negative for 11. So this equation, the positive and negative are switched from the opposite, the previous equation. So one of the interesting things that the book said was that could you be going so fast in your car that the red light was actually shifted to a green light? So it'd be blue shifted if you're going fast enough towards it, squishing up the waves. And you would have to be going so close to the speed of light that you would probably be breaking the speed limit anyways. Definitely be breaking the speed limit. So the amount of speed that we're moving here on the Earth is not really going to change how we see other light being projected from there. If we're looking at stars, that's far enough away with probably enough distances that we can decide that it's, red shifted or blue shifted. But with like a stoplight in this car, not going to happen. All right, I have a practice for us, and then I think I have 6 clicker questions. We probably won't go through all of them. How fast is a planet moving towards us if its oxygen emits a frequency of 5.85 times 10 to the 14 hertz, but we see at a frequency of 6.8 times 10 to the 14 hertz? Okay, so what is this 5.85? It is a frequency, and is it the one that we observed, or is it the one that originally is emitted? It's the original one, so we'll just leave it as F. What does that put the 6.8 then? The observed, so frequency observed. And is it getting closer or further away? Towards us. So we want the frequency one, which is F observed equals 1, and we want plus or we want minus? You guys remember? We'll look at it again. So it's getting closer, plus. All right, and then V, that's what we want to know. How fast is it going? Over the speed of light, 3 times 10 to the 8. Oh, wait. I forgot a few things in my equation. Oops. Frequency observed, 6.8 times 10 to the 14 equals the original frequency, 5.8 times 10 to the 14, and then the rest of the stuff that I wrote. All right, let's figure this out then. You want to know a shortcut when you do this first one, since they're both 10 to the 14, you can just do 6.8 divided by 5.8. 0.17. 1 plus v, 3 times 10 to the 8. So we're going to subtract 1, we get 0.17. And then multiply it by 3 times 10 to the 8. And you get 5.1 times 10 to the 7. So, pretty fast. All right, let's look at our other one. It says, how fast is a star moving towards us if the wavelength is shifted 35 nanometers from the original wavelength, which is 312 nanometers. So we have 32 nanometers and 312 nanometers.
35.
35, thank you. I don't know. It's just messing up a bunch today. Glad you guys are on top of it. 35. So what's this 35 nanometers? Let me look at the equation again.
The final loop.
It says that that's how much it's shifted. So what would it be? The change in wavelength. This is delta wavelength. And then what is this 312? Oh, wrong way. Let me go back. There we go. What's this 312 nanometers? The initial wavelength. So it's the original, which we'll just call wavelength for now. And then is it moving towards us or away from us? Towards. Okay, so looking at the equation, we'll use this part of it. Delta wavelength equals plus or minus the wavelength over V over C times wavelength. There we go. So delta wavelength, 35 nanometers. And when it's going towards us, do we want positive or negative?
Positive.
You want negative. Remember, this one's opposite. They're opposite in there. Pay attention to that one. So negative. The velocity, that's how fast we're looking for, 3 times 10 to the 8. And the original is 312 nanometers. Now, as long as you have nanometers here and here, you don't actually have to put 10 to the 9, 10 to the negative 9, because they're going to cancel. So you can leave it in nanometers, and it'll still pop out in meters per second. Just pay attention to your units. If you're not sure, change it. But in this case, it should be fine. So 35 divided by 312 gives me 0.112 negative velocity, and then 3 times 10 to the 8. And we get 3.37 times 10 to the 7 meters per second. Gives us our velocity, and that's negative. Okay, any questions? These equations are in your book, so if you get stuck on them, go and kind of read through that section. It should help you with using them. All right, I can do just a couple of quicker questions here. I don't think any of them are very hard. We won't get through all of them. So question 1, which of the following colors is not a primary light color? Remember, we're talking about light.